Systems of ODEs occur in the solution of many transient problems. In the previous video, we looked at using the native ODE solver and ease to numerically solve a single ordinary differential equation. This was accomplished using the integral command, which is shown here. Multiple integral commands can be used together to numerically integrate a system of coupled ODEs. Note that ease will evaluate the integrands of all of the equations together as it takes each integration step, and therefore it must use the same integration step size for each of the integrals as well as the same limits of integration. As an example, consider the two-mass system that's shown here. So let's consider the case where the top mass is initially displaced from its equilibrium position and then it's released. And we're going to try to predict the position of both masses as a function of time as they return to equilibrium. The value of the masses and the spring and the damper constants are entered in ease. There are four state variables for this problem, and these include the position of the two masses, so x1 and x2, as well as their velocities, which we're going to call v1 and v2. Initial values for all of the state variables must be specified. In this case, mass 1 is undisturbed from its equilibrium position, and therefore x1 initial is 0. Mass 2 is disturbed by 5 centimeters, therefore x2 initial is 0.05 meters. And both masses are initially assumed to have 0 velocity, so v1 and v2 initially are 0. In order to implement any numerical integration technique, it is necessary to develop the state equations for the problem. That is, we must be able to predict the time derivatives of all four state variables, x1, x2, v1, and v2, given their values and the value of time. In order to develop our solution, we will initially enter arbitrary values for all the state variables and for time. The time derivatives for x1 and x2 are simply their velocities, so these state equations are pretty easy. The derivatives of the velocities are obtained from force balances on each mass. So a force balance on the top mass, mass 2, is shown here, and mass times acceleration then is the sum of the forces, which is shown here, and that provides the derivative of v2. A force balance on the lower mass, mass 1, is shown here. And again, mass times acceleration is just the sum of the forces, which provides the time derivative of v1. These equations are entered in ease, and solving then provides all of the state variable derivatives, as was shown here. Therefore, we have successfully implemented the state equations, and we can move on now to the numerical integration. This step of first successfully implementing and verifying all the state equations is very important when you're doing any kind of a numerical solution to transient problems. So now we can comment out the specified values, the arbitrary values of the state variables in time, and we can go ahead and implement the numerical integration. And that integration is shown here for all four of the state variables. We're going to approximate these integrals using the integral command, as shown here. Let's use the $integral table directive to create an integral table that's going to store the results for every time step. Solving then leads to the integral table shown here, and the position of the two masses are plotted as shown here. Notice that ease has selected time steps adaptively in order to maintain accuracy while being as computationally efficient as possible. However, you should also notice that the integrals are computed together, and therefore they're all utilizing the same time step and must also have the same limits. The settings used for the integration can be adjusted in the integration tab of the preferences dialog, as shown here, but it's probably better again to use the $integral auto step directive to set the integration parameters directly in the ease equation window, which is shown here. The subsequent video will show how we can use the ODE solver in ease to solve a partial differential equation by breaking it into a large number of ODEs that we then couple and integrate together.